Welcome all who have landed here to learn more about this amazing storage technology on Climb today called as solid state drives. So let's kick the whys out of our way as usual. Why should we learn about solid state drives? Well, to begin with, that is one of the prominent technology that we have seen after decades of the field, after decades of dominance of the field of storage systems by hard disk drives. So definitely it should have something in it that it challenged a well-known, very popularly used over a long term technology, hard disk drives, and it started replacing hard disk drives today in many of our consumer electronics. For example, if you are one of the user of MacBook, they do not have hard disk anymore. Rather, they are sleek because they have SSDs inside them. Also, SSDs have started kicking hard disk out in many data centers. In recent years, we are seeing more and more all flash data centers. That means these data centers does not have hard disk at all. Rather, all whole and their entire persistent storage depends upon flash disk drives, also called as solid state drives, also called as NAND-based solid state drives. So, well, this should give us enough reason to dive into that, to learn about the problems that this new technology is been giving us, right? And to learn about how people have been successful in solving these problems so that now we can hold the beacon together and maybe we can solve the emerging problems of the next generation storage technologies, right? Okay, so to start with, the benefits of SSD, as we have already learned about hard disk, or many of you would be very well aware of what hard disk is, how does it work. So comparing the benefits of SSD with hard disk, well, SSD does not have any moving parts. And this is a big, big advantage because most of the faults and the failures that we saw earlier in hard disk arise from its moving parts. For example, the hard disk head could crash. Basically, it could just get stuck on the disk. Maybe the actuator or the motor, the rotatory motor, would over time would have some mechanical wear and tear that it doesn't rotate at the speed that we expect it to, it slows down, and all other issues because of environmental parameters such as things could rust, things could break, things could spoil. If you drop an hard disk, definitely there are chances that you would break one of the tiny mechanical part, and then that would end up that hard disk being not usable anymore because it's just that that tiny mechanical part was very critical to read and write data to that disk on the hard disk. So having no mechanical parts or no moving parts within the SSD is a big, big plus. Now, this makes SSD very similar to some of the popularly well-known memory drives, right? Like DRAM, it doesn't have any moving parts. SRAM, it doesn't have any moving parts. But the key advantage of SSD over DRAM or SRAM is, well, SSD provides us the persistence guarantee. So if once we put some data in there, even if there is a power loss, the data does not get lost. The data stays there, so we can come back to it anytime and then recollect or read the data or use the data, whatever we have stored before. Second, SSD provides us much high IOPS and IO concurrency compared to hard disk. This is just because moving things around when with a hard disk that has physical parts or moving parts, it just takes time, right? It takes time to take an object from one place and place it into another. So as we learned while learning about hard disk, or again, as you would have already known, we have latencies like seek time, rotation time, These both compose a great chunk of other delays apart from doing useful work while we are using hard disk. But now in SSDs, as we no longer need to seek or we no longer need to rotate anything, so well, that's these both is directly zero. And that's how we could get a better performance, better IO per second rate. As well as SSD, as you see here in this little diagram towards the right, you see that we have multiple NAND flash memory, and they get together to on a single chip of SSD. Each of these NAND flash memory could definitely be accessed in parallel, and that's why the concurrency that we can achieve while using SSD could be higher than while using a hard disk. Also, within a single NAND flash memory chip, there are ways in which we could extract parallelism with some caveats again. We cannot write and read all the data in parallel, but taking care of few aspects, we can still exploit parallelism at the chip level as well as at the multiple at the SSD level itself. Now, because of its no moving parts, an additional benefit is also low latency. Every IO can be done very quick compared to the time that IO took on hard disk. It has a very low areal density. That means we can store more amount of data in less space. Does an SSD that is of size of terabytes could just fit on your palm. It is very sleek, very lightweight, and does the sleekness or lightweight characteristics of modern electronic devices such as MacBook Air. That SSD is a main parameter that contributes towards that. Finally, SSDs consume way lesser energy and power compared to hard disk because much less work to do. Imagine the effort that it takes to physically move a substance from one place to the other versus an effort that it takes to move an electron from one place to the other. Way lesser in terms of electron, right? So that's the difference between the power or the energy consumption between hard disk and SSD. Now, packing all those benefits into our pocket, moving forward to, well, if SSD was everything good, then it would have already replaced hard disk long back, right? The year, does anybody know what was the year in which NAND-based flash was invented or NAND-based flash was put forward to other people? Well, it was in 1980s by a scientist called Fujio Masuka. So since 1980s till today, we have not yet made SSDs as the one and only form of storage, persistent storage that exists in every system. So that intuitively should make you think that there should be some challenges in how to use SSD or how to get the best performance, the least cost, and highest reliability from SSDs. So let's jump into those intricacies and challenges. Now, many characteristics of SSDs are just adopted from the characteristics of NAND flash cells, because the major component that stores the data within SSD is NAND flash cells. They get together in a group, bunch of them, and that's what makes this storage drive. So some of the challenges or some of the problems or some of the characteristics that are different from how we store data on hard disk, or how we are used to store data on hard disk, that SSDs bring forth to us because of just how it is constructed are, first, it has different IO units for read, write, and erase. Now, as you see here, I do not mention just read and write. I also have this third operation called erase. While most of the time, while discussing about hard disk, we talk about just read and write, not about erase. This is because hard disk allows us in-place update, where let's say if you write data A at location X, and if this data A is updated to data A prime, then exactly at the location X, we could just put that A prime, the new version of the data, in place of data A. While SSDs, or NAND SSDs, NAND flash-based SSDs, they do not allow us to do in-place update. And one of the requirement of SSD is we have to perform erase, which is clear of anything that existed before we can reprogram it with new information, or before we can add new data to an location where something existed prior to this. Thus, we have those three different operations, read and write. Those both operations could be done at the granularity of page, where we can read every page, we can write every page. While erase operation can only be done at the granularity of block. A block is a terminology used while discussing, or while we talk about SSDs, which is a combination of multiple pages. Now, please do remember that this block is different from the block that we talked about while discussing hard disk. It's just that, well, everybody in the world don't talk to each other, right? So while these new terminologies or new technologies are getting invented, such as while SSD was getting invented, some people used, to the best of their knowledge, what they thought would be good to explain some component. So these terminologies were called by humans, and one human is different from other human. And that's why it's just an overlap of few terminologies which might mean different in different context. Please be mindful of that. So while we are discussing about SSDs, or NAND-based flash drives, there we have this accumulation of multiple pages that constitute a block. Erase can be done. If you want to erase, we have to erase whole block. But if we want to read or write, then we can read or write an individual page. Now, because we have to erase before we can read and write, I think many of you would have already started thinking about the problem that actually could happen when we have applications or workload that are performing read-write operations simultaneously. It could happen that, well, we wrote a page inside the block, we write this page, then we want to, let's say we write content A into this page. Now we want to update this content with A prime. We cannot directly just replace this page with A prime. Rather, because we cannot do in-place update. So in order to write this A prime, we would have to first erase whole block. But unfortunately, this block also consists of other pages that might be storing something else that's important to you, like storing B in this other page inside this block. And erasing this entire block would lead to the deletion of this B. And you don't want that, because that's the data loss, right? You don't want to come back one day to your computer and see that, well, all your files are just lost, just because the SSD had to do something internal operation. So people expect reliability and fault tolerance from persistent storage. So that's just not an option. So what we might have to do is anything that's important in this block, we might have to copy that to another empty block. So let's say that we copy this data B that's important to us in the second block, the page of the second block. And then now once we are sure that nothing important is lying in this block, then we can erase this entire block. Once it's erased, then we can place this new version of A, which is A prime, inside this page of the block. So imagine these many operations that we have to do even for the simplistic read, write. So when an actual workload is running, how complicated the situations could become, right? The internal overhead that might not be a result of how workload is or what application is, but it's just the result of the way SSD is. We will discuss how we have over time, how we have learned to encompass or overcome many of these challenges. So that's the interesting part to come in this lecture. But quickly going over some of the other disadvantage of SSDs, or some of the other, better to call them as challenges of SSDs, because with every new thing, we always have some new challenges, right? SSDs have so many benefits, so it comes with its own set of challenges, and it's upon us how do we deal with these challenges to make use of SSDs. So the third thing is, because we have this internal data placement or data replacement that we have to manage, like in this example, we rewrote this page B to a new location. We have some internal write amplification, which is not the result of the workload writes, but these are additional writes that we have to do to just manage the data inside SSD. And why would these additional writes be significant for us to even mention about them, right? That's because SSDs or NAND flash cell have limited number of write cycles. We also call it as limited number of PE cycles, which is limited number of program erase cycles. So every NAND cell has certain amount of program erase cycles over which it can successfully sustain the data that's stored inside it as persistent data. After that many number of cycles, it could happen that this NAND cell might not store the correct information, or it may not at all store the information. We will also briefly see the reason behind this limited number of PE cycles, but just to give you an idea of how many or what is the limit, one of the best technology of SSD, also called as SLC, single level cell, we'll look further into what SLCs are soon. But SLCs are one of the good, let's remember that they are the best way how we can make SSDs, and they have a PE cycle limit of 100,000, around 100,000 PE cycles. So you can get an idea of how much important it is to carefully do this arrays and programs on your SSDs and ensure to limit them as much as possible. So if a workload wants to write, well, if it's a persistent storage, I don't think we have an option of saying no, right? But at least what we can do is, if we can limit the internal additional writes that we are doing, then that's the best, right? So minimizing write amplification as much as possible, that would enlarge, or that would make our SSD live long. Finally, one other challenge that SSDs provide is read disturbance or program disturbance. These are called disturbance errors. These disturbance errors happen because of either sustained, repeated reading or writing any particular cell. And that sustained recurrent reading or writing of a particular cell could impact its neighboring cells. And because of that, we might have stored some data into the neighboring cells, but when we come to retrieve that, the bits might have been flipped. Everything in terms of data storage inside a storage device is zeros and ones, right? So if you're supposed to have one at a location, and when you read that, if it's flipped to zero versus vice versa, if you're supposed to have zero at a location, if you read that, if it's flipped to one, then it's a big problem, because it would eventually mean just that one bit flip eventually means the data that you have stored no longer is that data. So if this error happened because of read, they are called read disturbance. If this type of bit flips happens because of writes, they are called write disturbance. So, well, as this tiny cute cartoon at the bottom says, write cycles of my dear SSD is about to get over. We do not want to be in that situation, right? Because then we know that this SSD can no longer be used. We would have to replace that. A new SSD means new cost, so on and so forth. So let's do our best to extract as best performance as we can from an SSD, as best reliability or fault tolerance that we can extract from an SSD at the least possible cost. Well, cost is something that we can just have an idea from the manufacturers of SSD, but not much that we control. But definitely as researchers, we can much work on these two aspects. And then you can some days go out there, set up your own company, and you can also work on minimizing the cost as well.